Hello class, this begins our second week of lectures, and today we're just going to derive the Lorenz Transformation. Okay, so again I said we were going to derive the Lorenz Transformations, but I just wanted to review a little bit. Remember, we had said that Einstein came up with a postulate. He said all the laws of physics, which at that time were just classical mechanics and electromagnetism, were invariant. Now I should say, if I really want to be correct, I really should say covariant. I just use invariant all the time. Usually if it's like one term is the same in all frames, then you would say it's invariant. If it's an equation, then that's what they call covariant. But if they're both the same, I'm just going to say invariant from now on. So, which meant that you cannot determine who is moving between the two observers, or you could not measure an absolute motion. Now, Einstein said he had to change one of them, either classical mechanics or electromagnetism. He said electromagnetism was the correct one, and he'll change classical mechanics. So he put in a second postulate, right? He assumed E and M was correct, and now he has to change classical mechanics and the Galilean Transformation. So he put in a second postulate. He said the speed of light is a constant in all frames, which really means that the speed of light is independent of the speed of the light bulb. If the light bulb is moving at 99% the speed of light and it emits light, it's still the speed of light right here. Now these were the transformations for the Galilean transformation. Actually, here were the actual equations for it. Remember, we had these equations. And this was what it was graphically when we plotted x versus t. The only thing we had was the constant x value shifted this way right here, whereas the times were right on top of each other. But last time we showed that if you're going to assume these two postulates, then this is what happens to this equation. Remember, we changed this from just t to c times t, because c is just a constant. And so what it did, it tilted it this way, and at the same time tilted up. They both tilted up right here, the same amount right here. The faster you go, the more this is just going to be tilted up. So if you had a point here, in the black coordinate system, it would be x, ct, and in the red coordinate system, which is this way, would be x prime, ct prime, right here. And the Lorenz transformation is the transformation that goes between these and back, forth. And if you were happen to actually move an object along here, we actually call that the world line. So when Frank was just going straight up, that was his world line going straight up right there. Okay, so that is just our review right here. Okay, so now we have a graphical example using this special relativity. So what I have here is I have a supernova. This is Frank's frame right here. That's his space, there's his CT. And we have a star right here, and the star is going to go up, but this star is about to go supernova. It's going to go supernova right there at that point. And we have a planet right here that's nearby. Here's the planet, and again, that's at rest relative to us. And it says this planet needs to be, there's people on this planet, and they need to be evacuated. So the Enterprise, right here, is moving to save these people. Now here is the x prime and ct prime. The axes have moved in, warped inward. We already said that x prime and ct prime right there. And so they're heading off. There's the Enterprise going off in this direction right here. Okay, and so the question is, and it says, when they get close to the planet right there, they can just beam them up and keep going right here. So we're just going to see what happens right here. So first of all, they say at which space-time point labeled A, B, C, D, E, F, G, or H does the Enterprise arrive at the planet? Well, here's the Enterprise. It's going along this way. the planet is this way, and it looks like it arrives right at point E. Okay. In the frame moving with the Enterprise, which is this frame right there, at which space-time point is the star when the Enterprise arrives at the planet? Well, when the Enterprise arrives at the planet, remember, these are equal times on the Enterprise right here. This is Mary's equal times. And so when the Enterprise reaches point E, the star is back here at A, and the star has not supernovaed yet. Okay, in the Enterprise frame, does the Enterprise arrive at the planet before the star goes supernova or after? Well, it looks like when he gets there, this point hasn't supernovaed yet, so it's before the supernova. Now, what about in the Frank's frame, in this frame here, the people that are there? What has the star gone through supernova? Well, in the Frank's frame, these are equal times. And so at E, you're way over here, so the supernova has already occurred from the people on the planet right there. Now it says, now do the students, or whatever who was there, the people there, do they see the supernova explosion before they get picked up? Well, the supernova, remember, the light from the supernova goes off at 45 degrees, so it's out this way. So even if they didn't get picked up, they wouldn't have seen the supernova until C right there. But it picked them up at E, so they were well away before the supernova occurred. Even though from the fixed frame, the supernova occurred first, but the light didn't get to them yet. Okay, so again, these are equal times for the moving frame, and these are equal times for the fixed frame right here. Okay, so graphically we can do all this without doing any of the math. Okay, now we'll go back to deriving those equations. So now we want to derive the Lorenz transformations, which would be similar to this, but this again gave me the other picture. So how do we go about deriving this? Well, we know that this has got to be pretty close. Why? Because it's survived for hundreds of years. So what we can do is, let's assume that it's very close to this. Let's just assume that we have x prime equals x minus vt, just like we did before, but let's just multiply it by a factor right there. We know it's just some factor in there. We'll have to figure out what that factor is. And we know that if we go the other way, x, it's going to be gamma prime x prime plus vt prime. Now, first of all, we can say a few things about this. We can say that these two equations should be symmetrical. Otherwise, you would know who is moving. So that gamma and gamma prime should be the same. That is, gamma should equal gamma prime. So we can get rid of the prime there. Something else we can also say. We can say that gamma cannot have an x or a t in it. If gamma had an x or a t in it, let's say gamma, let's just say it was x or t or whatever, you notice when we multiply this through, we would have an x squared. This equation must be linear, because if we're going from, say, Frank's to Mary's frame, and then Mary's to, let's say, Stan Speedy's frame, the sum of those should be, you go straight to Stan Speedy's frame. So, and if you had a square in there, that wouldn't work that way. Going from frame A to frame B plus from B to C should be the same as A to C. And so you can't, this thing has to be linear, which means that it can't have an x or a t in it, right there. Okay. So, we can also say that both of them should see the speed of light as the speed of light. So Frank should say this light is going out at CT, right here. If he just looks at a beam of light, it should just be the V times the T. And Mary should be saying the same thing right there. So why don't we write it like this? CT. They both should measure the speed of light the same. Okay, so now, this is all we need right here. So now we can do is, let's take all of our x's and x primes up here and plug them in. We'll plug this into here and into here, and we'll plug this into there and there. So up here we get CT prime equals gamma x, which is CT, minus VT. And over on that side, we'll plug in these two x's. So x, which is CT, equals gamma x prime, which is CT prime, plus VT prime. Okay, now what I'd like to do is solve for one of the t's and plug it into the other one. I don't know if it matters which one I do. I guess we'll just solve for t prime here, and we'll plug it into those two spots. So right here, t prime is equal to gamma over c, ct minus vt. And we'll plug it into both of those two spots. I think before I plug it in, why don't I factor out the t prime out of these two? So right here we would get ct equals gamma. I'll pull the t prime out, t prime, c plus v. Now I'll plug that t prime into there. So we get ct equals gamma times all of this. I think I'll pull out the t out of here. So this is gamma t over c. Gamma t over c. And then we still got the c minus v left. C minus v, and we have this c plus v. Okay, and so now we can cancel out the t's. Right there. And I think maybe I'll bring the c up here, so we got c squared equals gamma squared, and then c minus v times c plus v is c squared minus v squared. And then we'll divide out the c squared minus v squared, so gamma squared is equal to c squared all over c squared minus v squared. I think I'll take the c squared down below. So gamma squared is equal to 1 all over 1 minus v squared over c squared. And then last step is take the square root of both sides. So gamma equals 1 all over the square root of 1 minus v squared over c squared. So now we know what our transformation equation is. For x prime, we just plug that in. So x prime is what it was before, x minus vt, all divided by the square root of 1 minus v squared over c squared. Now, first of all, if we were to plot this out right here, so this is gamma, and this is v, how fast we're going. When v is very small, this thing better be 1, because the two are the same when you're going slow. Well, when v is small, v squared over c squared is pretty much 0. 1 minus 0 is 1. Square root of 1 is 1. 1 over 1 is 1. So when you're small, this is just 1 right here. So it's just right there, just 1 right there. Well, now what happens, you start going a little bit faster right here. Let's say you get up to a million miles per hour right here. This is 10 to the 6 miles per hour. That's pretty fast, a million miles per hour. Well, if you plug in this right here, a million, this million is still small compared to this right here. This number goes up to about 1 point, it's just a little bit higher. It actually, if v is equal to 10 to the 6th miles per hour, that gamma is 1.12345. So there is, I don't know how to draw that here. It's still pretty much 1 right there. Okay, and if we go up to 10 million miles an hour, it's still 1.001. So even at 10 million miles an hour, it's very tough to see right here. So if v is 10 to the 7th miles per hour, gamma is still 1.0001 right there. So again, it's still flat right there. Now what about, what if we get all the way up to half the speed of light, which is 350 million meters per second? So if this were 350 times 10 to the 6 miles per hour. That's about half the speed of light, and that's still, gamma is just 1.15. It's only grown by 15%. So even at half, let's just say this is c over 2, you've just barely gone up right there. So it's just barely gone up. Now we can see right here that if you're the speed of light, then this is 1. 1 minus 1 is 0. You get a 0 in the denominator, which means you get an asymptote. So there is an asymptote. Actually, it's at c. I guess I should be out a little further. If that's c over 2, then, it's, let's just say there's my asymptote right there. So this thing is going to just kind of head on off this way. And you might say, well, how fast do I have to go before gamma gets to twice this big, to 2? Right there at 2. How fast do I have to go to get to 2? Well, let's just come over here and set this equal to 2. So if you put this as 2, we get 2 equals 1 all over the square root of 1 minus v squared over c squared. And we just solve this for v. Let's square both sides. So we get 4 equals 1 all over 1 minus v squared over c squared. Let's flip both sides. So 1/4 equals 1 minus v squared over c squared. Bring this over, take the 1/4 back, so v squared over c squared is equal to 1 minus 1/4, which is 3/4. Or v over c is equal to the square root of 3 over 2. Or v equals the square root of 3 over 2c. And since you already know what the square root of 3 over 2, every time you take the cosine of a 30 degrees, that's just 0.866. So this is 0.866c. So if you go at 86% the speed of light, this factor, it goes up to 2 right there. So this is 86. We're going to use this a lot because it's a nice number to use. The square root of 3 over 2 means that gamma just becomes 2. So let's maybe I'll just write it as the square root of 3 over 2 C, or 86%. 86% C. Okay, now that gives me the transformation for the x right here. Now what's it going to be if we go the other way? That is, if this is the unprimed and that's the prime. Well, what did we say the rule was? We said we switch all the unprimes with primes and primes with unprimes, and we change the sign of v. So if we do that, then we get x right here. We could say x is equal to x prime. That changes the sign, which is plus vt prime all over. We don't change this sign because v is squared. Minus v squared is still the same thing right here. So if you just change the sign of v, it still stays the same. So this is still the square root of 1 minus v squared over c squared. So this is going from Frank to Mary. It's going from Mary back to Frank right there. So that's for x right there. Okay, y is still going to be the same. Y and z, y is still y prime, z is still z prime. These are still the same. But we already know that t is not t prime. The t's are this way on one frame and they're this way on the other. So we need to figure out what is the transformation for the time right here. Okay, well, let's take, why don't we take this x right here and plug it right back up into here. We'll do that right there. Okay, so if we just take that x and plug it up in there, we get x prime equals we get x, which is all of this, x prime plus vt prime, x prime plus vt prime, all over the square root 1 minus v squared over c squared. So that's my x, sorry, that's my x, right? That's right. Minus vt, minus vt, plugging it into here, all over this term right here. All over the square root of 1 minus v squared over c squared. Okay, so let's solve for t out of this, because everything on the other side will be primes. So let's first multiply this term, bring it up to here. So we got x prime times the square root of 1 minus v squared over c squared equals just the numerator here. X prime plus vt prime all over the square root of 1 minus v squared over c squared minus vt. I think what we'll do is I could even multiply this by every term. So I just get rid of the fraction right here. So this term over here will be x prime. This times this will be just 1 minus v squared over c squared equals x prime plus vt prime minus vt times the square root of 1 minus v squared over c squared. Now, if I were to multiply this through, you notice right here we get an x prime, and over here I get an x prime. So I can eliminate the two x primes. That is, this term and that term is going to cancel. Right? So this becomes minus x prime v squared over c squared equals vt prime. I think I'll move the vt prime to this side so that it's minus vt prime. And that equals minus vt times the square root of 1 minus v squared over c squared. Now I can get rid of all the minus signs. And we can get rid of at least a v in every term. So if I rewrite that, we get x prime. I think I'll put this term first. We get t prime plus x prime v all over c squared equals t times the square root of 1 minus v squared over c squared. Or t equals this divided by that. So it's equal to t prime plus x prime v over c squared plus x prime v all over c squared divided by the square root of 1 minus v squared over c squared. So that looks like, that's a lot different than before. Before it used to be just t equals t prime. Now it's this, right? And if we were to go the other way, this is from Mary to Frank. If we were to go from Frank to Mary, then we'd had we could just t prime then would equal, we switch the primes, the unprimed, so that's t. Switch the sign of the v, so that one's subtracted, minus x v all over c squared divided by the square root of, this still stays the same, v squared over c squared. So these are our time, a lot different than they were before. That's what gives us a little tilt right here. So you notice the time is not only dependent on the speed, but it's also dependent on the position of the other one. So you remember when we had, this was our Frank coordinate system. Let's just say there's our Mary coordinate system right there. If I were to just draw 3 points here, let's say this point, and this point, 1, 2, and 3, these 3 points would be equal in Frank's frame right there. But in Mary's frame, they would not be the same. These 3 times would be different. You notice the bigger the x, we're going from Mary to Frank, which would be this one up here. This is Mary to Frank. You notice that the bigger the x is, actually, let me take that back. When we're actually in this one right here. If this is Frank's frame, that's point 3 is in Frank's frame. If you want to go to Mary's frame, you'll notice that the bigger the x is, this gets smaller and smaller right here. Because remember, these are earlier times. In Mary's frame, these are earlier times, these are later times. Right? So the time is just a function of space too, right here. That's why there's an x over there. And we can see when x is small, when v is small, this term is 0 and that term is 0, and you get what we had before, t prime equals t. So we can see that, usually we only notice this when v gets large. But according to this equation, we might be able to see it even if v is not large. What if x were really large? If x were really large, v could be small, and there would be a time difference. So if we looked at it for a very small velocity, let's just say here's for a very small velocity, then this is barely tilting in. It's just barely tilting in right here. And you might say, well, you wouldn't notice that unless x is really large. So if this were, I don't know, to the edge of the universe right here, then just walking, we'll see later, can really affect the time over these 2 points right there. Okay, so this is the derivation right here. So we're going to be using, instead of these Galilean transformations, we're going to be using the Lorenz transformations. And on the next lecture, we will start to see some of the outcomes of using these transformations. Okay.